be. Do you know topic or?
I think so, but he's hostile then.
Okay. Okay, yeah, we can also start slowly and then people can come in. Okay, so hello everyone. We are very happy to have Mark von Raamsdonk today as our seminar speaker. Mark is a professor at the University of British Columbia. He got his PhD from Princeton University before joining actually Stanford in 2000 as a postdoc, and then 3 years later, he became a professor at the University of British Columbia. And his work covers different aspects of quantum information and cosmology, and especially how to connect these two theories in quantum gravity or another like via this ADS-CFT correspondence. And when you look up Mark, you also find soon that he has a very broad interest in physics, which also, despite being a theorist, he has some experiments which you can check out on YouTube, on his YouTube channel after the seminar. So with that, we are very happy that you are here, and please take it away.
Okay, well, thanks a lot for the invitation, and I'm sorry I'm not able to be there in person and have to subject you to another virtual talk, but hopefully we'll enjoy it. So the topic is related to cosmology, and maybe this is an odd topic for this seminar, but it turns out the last month or 6 weeks, I've basically been working with lattice fermions and investigating a particular question in detail. And so I thought that would be sort of appropriate for this talk. And so the order of the talk is going to be kind of the reverse order of the title. I'm going to introduce some question related to cosmology, say how that's connected to wormholes and the negative energy. And then the last part of the talk is going to be this investigation of what kinds of negative energy are possible in just an ordinary kind of quantum field theory system, just a free fermion. So this is all work which I've done in collaboration with various people. Most recently, a graduate student, Stefano Antonini, and Brian Swingle, and my student, Peter Simidzija, and also Brian Swingle. And then the last stuff about the fermions is with Brian. Okay. So my background and main focus is in quantum gravity. And so, there's been a lot of great progress in quantum gravity in the last, say 20 years in my career, specifically through this string theory approach of using holography, of realizing that certain quantum gravity systems are exactly equivalent through a duality to more ordinary quantum systems, quantum field theory systems, or even simple quantum mechanical systems with many degrees of freedom. And so, of course, perhaps one of the main reasons why you would want to study quantum gravity is to, say, come up with some understanding of the Big Bang or the early universe, or cosmology, which is, say, one of the places in our universe where you probably can't just get by with a classical understanding of gravity. Okay. But a lot of the progress in this holographic approach to quantum gravity has not, most of the progress has not really touched on cosmology. And there's, I think, a couple of reasons for that. One of the reasons may be that I think there's perhaps a misconception, but an idea that, ADS-CFT is not going to be very useful for cosmology because the kinds of spacetimes that we can study using this approach, they tend to be spacetimes with a negative cosmological constant. Okay, so the ADS in ADS-CFT refers to this spacetime with a negative curvature that comes by solving Einstein's equations with a negative cosmological constant. And if we look at our universe, observationally, it's at least lately been accelerating. And the simplest way to explain that acceleration of the scale factor of the universe is that there might be a positive cosmological constant. So it looks like a kind of a different regime of quantum gravity than the regime that we can study well using this holographic approach in string theory. But I want to actually start by just reviewing a little bit the observations and what they actually tell us. So I want to question maybe this this idea. So as I mentioned, the observations are that, well, first of all, the universe has been expanding. If we look at the redshift of various stars and galaxies, we've known for a long time that the universe is expanding, and more recently, since '99, we've actually understood that at least presently this expansion is accelerating. And so if you take that observational fact and then ask, what does that tell us about the matter in the universe? So you have the scale factor in the metric has a positive second derivative. You plug this into Einstein's equations, or more specifically, the Friedmann equation for cosmology. And it tells you something about the stress energy tensor of the matter that would be causing this acceleration. It tells you that 3 times the pressure plus the energy density is less than 0. So there's a couple of ways that you could explain that. Perhaps the simplest way is to have a negative cosmological term in the Einstein's equations. Okay, so negative dark energy, or lambda greater than, or sorry, positive cosmological constant, I should have said. But you could also explain this sort of acceleration if you have scalar fields in your theory, and if you have a potential for those scalar fields, which at the present time has a positive value. So that's kind of a more general way to end up with this constraint being satisfied. And I guess one, really, you could think of it as a special case of 2. So in fact, we believe that there are scalar fields in our description of nature, so the Higgs field at least. And so in the standard model Lagrangian, there's some potential for scalar fields. And the usual assumption is that we're just at an extremum of this potential. And so if you have scalar fields with a potential and you're at an extremum of the potential with a positive value, that's like having a positive, that's the same as having a positive cosmological constant. Okay. So 1 is kind of a special case of 2. But it's interesting to consider the more general possibility. Okay, so in fact, if you're just trying to describe the observations kind of naively, if you wanted to write down the most general background, so meaning the most general, like classical configuration of metric and other fields that would be consistent with the symmetries of cosmology, well, then you would have, so we have a time-dependent scale factor, and then also having time-dependent scalars wouldn't break any further symmetries. So in a sense, it would be natural starting out to consider this possibility of having scalar fields that are time-dependent, as well as the scale factor that's time-dependent, and then try to constrain that time dependence. Okay, so let's imagine that possibility where we have this scale factor, it's expanding and accelerating, and let's imagine that that's actually due to the potential for some scalar fields being positive at the present time, but let's imagine that these scalar fields might be changing with time. Okay. So if you look at how do scalar fields change with time in cosmology, there's actually a very simple analogy. So you have a potential for these scalar fields, and the equation of motion that governs the time evolution of scalar fields is just the same as the equation of motion for a particle in this potential, with some damping that's given by 3 times the Hubble constant, 3 times the A dot over A. Okay, and so typically these scalar fields would be moving towards a lower value. So if you have a particle and a potential with damping, typically they eventually end up at lower values. And so if we have this currently positive value, which is observed to be actually quite tiny relative to, say, the Planck scale, and we know that and if that's going to be decreasing with time, then it's pretty reasonable possibilities that sometime in the future, then that value of the potential would end up being negative. Okay, so if we're moving towards perhaps some extremal value of the potential, then of course it could be a positive value that we're moving towards. It could be 0, but in terms of like the space on the real number line, the largest set of possibilities would be negative values that we're moving towards. Okay, so given our observations, we have various possibilities to explain those. There's this lambda greater than 0 possibility, and then there's the possibility that we have time-dependent scalars moving in some potential. And we've seen that, well, in that case, say the extremum that we're moving towards might have a positive value or a 0 value or a negative value. Okay. I mean, I should mention that there are definitely some constraints on the shape of such a potential. We know that the dark energy, or this dark energy, is not changing too fast. And so I should point out that there are constraints, but anyways, all of these possibilities, I think, can be made to work with observational data. Okay, so now we can ask, if we're taking the point of view of trying to come up with some holographic model of cosmology, or some, say, string theory model of cosmology, some kind of microscopic model of cosmology, which case should we focus on? And just if you look at string theory as a model of quantum gravity, the kinds of 4-dimensional effective field theories that you typically get when you start with string theory and compactify to 4 dimensions, well, you typically get plenty of scalars around in the effective field theory. And as I mentioned before, we do have this beautiful microscopic understanding of physics of quantum gravity in many situations with a negative cosmological constant. So I think, it's a bit surprising, given that if you look at a lot of the effort that's gone on in trying to connect string theory to cosmology, there's been quite a lot of focus on the lambda greater than 0 case. Okay, and perhaps that's justified. I mean, in a sense, that's the simplest possibility from the effective field theory point of view to describe our observations. But I think since lambda less than 0 is actually not ruled out, it's possible with these time-dependent scalars. And since we have such a better understanding of string theory and holography, like from a microscopic or non-perturbative point of view, when lambda is less than 0, then a good step at this point in our understanding of string theory seems to maybe be to try to describe these lambda less than 0 cosmologies. Okay. So can we come up with microscopic models of lambda less than 0 cosmology? Maybe we could even come up with some realistic scenario, but even if we're only able to come up with, say, some description of Big Bang cosmology with lambda less than 0 that's not realistic, that would still be a good step in our understanding of quantum gravity. Okay, because basically right now we don't really have any fully microscopic description of quantum gravity in a situation where you have a Big Bang and an expanding universe. Okay. So that's going to be the focus. I'm going to ask, can we use holography or string theory to describe a cosmology with negative cosmological constant and perhaps time-dependent scalars that could eventually give rise to acceleration? All right, so I said that string theory is pretty good at describing universes or space-times with negative cosmological constant using this holography or ADS-CFT approach. okay, where you have some non-gravitational quantum system that's equivalent to gravitational theory. But turns out it's still a challenge to describe cosmological spacetimes with negative cosmological constant. Okay, so cosmology is, in a sense, the study of spacetimes that would have stuff in them everywhere. Cosmology usually assumes that at the start that you have homogeneous and isotropic matter throughout the universe. Okay. Whereas these kinds of spacetimes that we're good at describing using the ADS-CFT approach, those are spacetimes that can have lots of interesting stuff in the middle. You can describe black holes and gravitational waves and all sorts of matter. But these spacetimes are typically, I would say, asymptotically empty, meaning that there could be lots of interesting stuff, but then if you go very far away into the asymptotic region of the spacetime, it's just empty, and it's this negatively curved ADS spacetime. Okay, so like the vacuum geometry with negative cosmological constant. Okay. So a different way of saying that is, like, if you study the cosmological spacetimes with negative cosmological constant and matter or radiation, these typically don't have any of these asymptotically ADS regions that we usually connect with having a dual field theory description. Okay, so here's an example of maybe the simplest negative cosmological constant cosmology. If you just add some radiation and you have flat geometry, then you get this really simple metric where the scale factor is just the square root of cosine. So if you look at that geometry, it has a big bang, it has a big crunch. This is like the space-time diagram, if you're familiar with those. And so the point is that it's just spatial. You can look at the spatial geometry, it's just an infinite flat plane, and there's no sort of asymptotically ADS boundary anywhere. Okay, so we get to this point where you get stuck in a sense. Even though it's a space-time with negative cosmological constant, you don't really know how do you connect that with some dual field theory. Okay, so this is a place where we can look for some kind of a hint. And so I'm again going to focus on this simple example of the cosmology with negative cosmological constant and radiation, just so we can look at an explicit metric. So there's a mathematical curiosity, I guess, or a fact that if I take this geometry and I think about complexifying the time coordinate. So if I think about, for some reason, if I take the time coordinate and consider imaginary values of that time coordinate, so I plug in t equals I tau into this metric, then I get a different metric, which is Euclidean. It doesn't have, it has all spatial directions, and which actually is asymptotically ADS. Okay, so you get this metric, which for tau equals plus and minus infinity, it's empty and it's negatively curved. And so it's exactly the kind of geometry that we normally have in examples of holography in the ADS-CFT correspondence. Okay. But it's an interesting sort of asymptotically ADS geometry because there are actually two different asymptotically ADS boundaries. So you might call this, sometimes people call this kind of geometry a wormhole. It connects two boundaries with space in the middle. And so this is like a hint that maybe there's some way to use holography to describe this space-time, and maybe that could be used somehow to connect with cosmology. But it's, at this point, it's just like a weird mathematical fact. And why would you want to consider imaginary values for the time coordinate? So let me remind you a little bit of some other physics where we do actually often consider imaginary values for the time coordinate in quantum mechanical systems. Okay. So in quantum field theory, actually even in quantum mechanics, if you have some quantum system, then it's possible to consider a Euclidean version of the same physical theory where you make the time imaginary. And these associated Euclidean theories, these are often used to define natural states of the quantum mechanical system. So if you've studied quantum field theory, then you know that the Minkowski space vacuum, a way to that's related directly to the Euclidean version of the same field theory on Euclidean space. So for example, the observables in the Minkowski space vacuum state of a quantum field theory, those are analytic continuations of observables in a Euclidean theory. Or sometimes we talk about the thermal state of a quantum system or a quantum field theory, and that's related in a way also through analytic continuation to a Euclidean theory where the time direction is periodic. Okay, so just that same Euclidean theory, but on a different geometry. And in gravity, there's a famous example of using the Euclidean version of a quantum theory to define a special state of the gravitational system. So Hartle and Hawking, they wanted to define a special state, a wave function of a gravitational system that might describe the state of the universe. Okay, and so their idea was to say, start with a gravitational quantum theory, like quantum field theory coupled to gravity. So that's a theory with ordinary time. Consider the Euclidean version of that theory, and then define a wave function for the original theory by saying that the wave function evaluated on some like metric and field configuration. So G, that denotes the argument of the wave function. They wanted to say the wave function of that evaluated on that configuration is, you think about all the possible ways of taking that configuration, say at the present time, and then filling in the geometry as thinking about that as the boundary of some four-dimensional Euclidean geometry. And then you sum over all those possibilities weighted by e to the minus the gravitational action. And that defines this Hartle-Hawking wave function of the universe. Okay, so again, an example where you take the Euclidean version of a theory and you use that to define a special particular state of the Lorentzian theory. Okay, so this physics then suggests a way to make sense of this Euclidean asymptotically ADS geometry that we got by analytically continuing this cosmology. So what it suggests is that maybe we could use this ADS-CFT approach or this holographic approach to come up with a holographic description, come up with like a microscopic fundamental description of this particular space-time or this particular gravitational theory, and then use that like Hartle and Hawking did to define a special state of the Lorentzian gravitational theory that would be our cosmology. Okay. So that is the idea. That is the basic idea. Okay, so let me kind of summarize that. Okay, so the summary again is that we live in a universe with time and gravity in various fields, and there should be some kind of particular gravitational theory that describes our universe. There is mathematically another gravitational theory without time that we can get from that by just taking time and setting it equal to an imaginary value. So there's this other theory that describes just spatial geometries. And so what we're going to imagine doing is trying to define this other theory using the ADS-CFT correspondence. Okay, and then we'll use that Euclidean theory, like Hartle and Hawking did, to define a special state of the cosmology, and that's how we describe the physics, maybe of our universe, maybe of just some artificial universe that has cosmology in it. Okay, so in practice, what we're going to do, to compute things in the cosmology, we can just compute quantities in this Euclidean theory using our fundamental description and then analytically continue them. So that's how we'll learn about cosmology through this approach. So I should just mention there's an interesting third geometry that we could talk about. Okay, so we got this Euclidean wormhole geometry by taking the original one, setting time to imaginary values. If we take one of the spatial directions of the original cosmology and set that to an imaginary value, okay, then we get a third kind of geometry that has a time coordinate and where the spatial geometry is this wormhole. Okay. So that's kind of interesting for our purposes, because this particular Euclidean gravity theory, so in just the same way that we said you could use that to define a special state of the cosmology by taking this spatial coordinate and setting that to be imaginary, you could also take the same Euclidean theory and use it to define a special state of some other Lorentzian theory by taking one of these spatial coordinates and setting that to be imaginary. Okay, so there's this kind of mathematical operation that allows you to start with a Euclidean theory and get a particular state of a related Lorentzian theory, but actually there's multiple ways to do that. Okay. And so the interesting thing is that on the left and the right, we have two sort of physical theories with ordinary times, both basically the same gravitational theory, but they're different solutions. And the thing on the right is just a really simple static space-time where all the fields are in their vacuum state. So the reason this is really interesting is that the observables in the cosmology, we said they were related by analytic continuations to the observables in this Euclidean theory, but they're also related by some further analytic continuation to the observables in this geometry at the right. So you have basically the vacuum physics of some quantum fields in this particular, what we call Lorentzian wormhole spacetime. And if you could learn about those observables on the right, those vacuum observables, and then just analytically continue them twice, you could learn about the cosmology. Okay, and so that is kind of the way that I want to set this up. Yep. Oh, was there a question? No. Okay. Okay. So we're going to. Oh, I'm getting an echo. All right. I'll keep going. So we're going to use string theory to precisely define the physics of 2 or 3. Both of those are asymptotically ADS, and we can use holography. And then we're going to compute observables there, analytically continue them, and that will teach us about the cosmology. Okay, so I'll just comment on briefly. I don't want to get too much into the string theory story, given the audience, but I'll comment briefly on what is this string theory description. And so we have, for this wormhole geometry, it's a thing with 2 asymptotically ADS regions. And we normally associate these asymptotically ADS boundaries, the geometry of those, with the geometry where the field theory lives. So the fact that you have 2 separate asymptotically ADS boundaries here suggests that your holographic description should involve 2 separate 3-dimensional holographic conformal field theories. The fact that you can go from one side to the other through the geometry, so this is what we'd call a traversable wormhole. This is just a static Lorentzian spacetime, the one on the right. That suggests that these 2 CFTs must actually be interacting with each other somehow. Okay, and so the proposal that we made, based on a whole bunch of other string theory motivation that I won't get into, is that to describe this sort of geometry, we need to start with a holographic conformal field theory that would be dual to asymptotically ADS spacetimes, take another one and then couple them somehow. What we ended up saying was we want to couple these by an auxiliary set of degrees of freedom that takes the form of a 4-dimensional field theory. Okay, so that's just a little bit for the experts. This coupling between those, it basically has a big effect in the infrared. Okay, so these are 2 3-dimensional conformal field theories. We couple them somehow to define like a new 3-dimensional field theory with this small 4th dimension, a compact 4th dimension. But then the infrared physics, the long distance physics, is again just going to be 3-dimensional. And the idea here is that this coupling actually induces an RG flow to a confining theory. Okay, so rather than being a conformal field theory in the infrared, it's confining. And the vacuum of this confining theory has a large amount of entanglement between the original 2 3D theories. Okay. This large amount of entanglement is reflected in the geometry by the connection between the 2 asymptotic boundaries. Okay, so that's the string theory bit. We won't really need that for the rest of the talk. So let me just then review the cosmology story. Okay, so what are we going to do in the end? So we have this particular 3-dimensional quantum field theory. Okay, this is like our underlying microscopic description. So this we can precisely define, and this somehow contains all of the physics of the gravitational theories. Using this, we could, if we want to, compute all of the observables or physics that we want to for this geometry here, which is the asymptotically ADS wormhole. So there's some gravitational solution which is described by this through the duality. And then what we want to do to learn about cosmology is compute observables here and analytically continue them. And those will tell us the observables in our cosmology. Okay, so for example, if we wanted to learn about the scale factor in the cosmology, how does the universe evolve with time, then what we can do is just try to find out what is the scale factor in this wormhole. So how does the metric change as you go from one boundary to the other? That will be some function of this spatial coordinate tau. You analytically continue that, and then you get the scale factor in the cosmology. If I want to learn about some correlation functions in the cosmology, for example, correlation functions that would tell me about the CMB, then I would just compute this, some related correlation functions in this wormhole geometry, analytically continue them, and that would tell me the correlation function in the cosmology. Okay. So you could, mostly when we're talking about cosmological observables, you could reduce those to certain correlation functions. Okay, so this framework, it should say, so far, I don't know if we can get realistic models out of this framework, but it does have a lot of intriguing features. So there are some kind of generic predictions of the framework. Any model like this, it's going to give you a homogeneous isotropic flat cosmology. It has the characteristic that the cosmology is time symmetric. Okay, so we know that our universe is expanding now. If our universe is described by this framework, the prediction would be that eventually it stops expanding and that it will eventually crunch. So we'll have like the opposite of a Big Bang sometime in the future. One of the really interesting features of this framework is that if you look at the kind of generic examples that would come out of this, they do tend to have time-dependent dark energy from time-dependent scalar fields. Okay, so in the kind of gravitational theories associated with holographic CFTs, you often have these scalar fields there's some connection between those and the operators in the field theory that are relevant, that have certain dimensions. And those scalar fields, those particular scalar fields do typically tend to change with time in the final cosmological solutions. And it's actually not too hard. It's fairly natural within this context to have those scalar fields give you a period of acceleration at late times in the cosmology before this crunch. So you can actually accommodate, even though the cosmological constant is negative in the whole scenario, you can accommodate a period of acceleration. That could be what we're observing. In these kind of scenarios, the underlying effective field theory is actually supersymmetric. So that can help with the cosmological constant. It's just the value of these scalar fields being away from their extremum that give apparent supersymmetry breaking, and they also give gauge symmetry breaking. And there's some interesting candidate explanations for various naturalness puzzles in cosmology that I won't have time to explain, but you can have a look at our paper. Okay. So what I want to focus on for the rest of the talk, though, is kind of a puzzle related to this whole framework. Okay. So it all sounds really nice, but there's some really weird feature that I haven't mentioned yet that basically comes in if all of this is correct. Then all of these spacetimes that I'm drawing here should be like physical solutions to Einstein's equations coupled to matter. And this Lorentzian wormhole spacetime that I was saying that we're going to compute observables in and analytically continue them to get our cosmological observables. Okay, so that kind of a spacetime is a little bit strange from the point of view of gravity and general relativity. And the reason is that if you look at the Einstein equation, and you just actually look at the Einstein equation in the middle of such a wormhole geometry, then it tells you that this is a particular component of the energy. This is like what we call the null energy, T++. That's a component of the stress energy tensor, where the indices are both in light-like directions. Okay, so this thing evaluates, according to Einstein's equations, to something in terms of the scale factor, which for a wormhole geometry like this is a negative value. Okay. It's not only a negative value, it is a negative value that is quite large relative to the geometrical scale of this geometry. Okay. So that geometrical scale comes in the derivative here. G is the Newton constant. So this number here is like in a sense, the size of the universe in Planck units, or the square of that. So it's a big number. And so basically to support this kind of wormhole geometry, you need this really large amount of negative null energy. And there are theorems in quantum field theory that restrict how much null energy you can have. Okay, so there's a theorem called the average null energy condition that says that if you take T++ and integrate it over a complete null geodesic, so from minus infinity to infinity in time, so like the path of a light ray through Minkowski space, then that thing has to be positive. So in some situations, you just cannot have this sort of negative energy. Now, in this kind of geometry, that theorem doesn't apply because you've got these asymptotically ADS boundaries. And so there isn't a similar theorem, but it still seems a little bit odd that you would have maybe states of quantum field theory in these wormhole geometries that can have such a big negative energy when that kind of negative energy doesn't seem to be allowed just in infinite Minkowski space. And so in a sense, this framework, if it's going to work, it suggests that there's a weird new thing that should be possible in quantum field theory. And this is the thing that I've been like trying to investigate the last several weeks or a couple of months. Okay. So the rest of the talk is just going to be field theory. And I'm going to be studying just a really simple field theory. So I'm going to be studying a free massless Dirac fermion on this wormhole geometry. So like a massless electron on this wormhole geometry. And I want to just try to directly ask, can this field theory have states with such big negative energy that would be needed to support this wormhole geometry? So because a free massless Dirac fermion, it actually has a conformal symmetry, a scaling symmetry. That as a quantum system on this wormhole geometry is equivalent to that same quantum field theory on just a slab of Minkowski space. Okay, so there's a conformal transformation of the metric where you multiply the whole metric by a factor. And if you have one of these conformal field theories, then the conformal field theory on two metrics related by such a transformation is that you can map between the states of those two theories. So they're in a sense equivalent as quantum systems. Okay. So in order to answer my question of whether we can get this large negative energy, I can just ask the question for the Dirac fermion on a slab geometry like this. So I'll imagine a particular spatial direction whose extent is distance L. And I'm going to ask how much negative energy can my free Dirac fermion have relative to the Minkowski space vacuum? Okay. So if I call the vacuum energy in Minkowski space 0 energy, how much negative energy can I have for this fermion on the slab? Okay. And actually, I'll be specifically just assuming that the negative energy is uniform throughout the slab. Okay, so there's a well-known example where you do get negative energies relative to the Minkowski space vacuum. Okay, so if I take my slab and if I were to identify the two sides and choose boundary conditions for the fermion going from left to right that are anti-periodic, so the sign flips when you go from one side to the other. With those boundary conditions, it's known that you have an energy density in the vacuum state that is negative relative to the Minkowski space vacuum. So this is like a Casimir energy for a periodic direction with anti-periodic boundary conditions for the fermions. And that energy density in units of the length of the periodic direction is this number, minus 7 pi squared over 180. Okay, so we can have some negative energy. It's these Casimir energies are the known way to get the kind of negative energies that you would need. But this number is, say relatively small. Whereas for our wormhole geometry, we wanted to be able to get a number here that is huge, or like, as big as we want. And so what I want to do now is ask, well, are there maybe other kinds of boundary conditions for this Dirac fermion on a strip that would allow me to have even lower energy, even bigger negative energy? And so the way that, and so the way that we wanted to do this is just to be agnostic about what is the physics past this interval. So I don't actually want to try all possible boundary conditions. I'm going to try to look at just all of the states of this quantum field theory on the interval without specifying boundary conditions. Okay, so from a quantum mechanics point of view, I basically want to explore the possible density matrices for this theory on the strip, and then ask if any of those, like how much negative energy can have in that space of density matrices. Okay, so the problem simplifies a little bit because with a free Dirac fermion on this kind of geometry, we can actually split it up into momentum modes in the transverse direction. Okay, so I can take my physical system and then write that fermion on the three-dimensional space as a sum of a bunch of different momentum modes. And the theory decomposes into those modes. So that theory of the free Dirac fermion in 3+1 dimensions is equivalent to a collection of 1+1 dimensional Dirac fermions 2 for each momentum because the 3 plus 1D fermion has 4 components and the 1 plus 1 has only 2. So basically your higher dimensional fermion just splits up into a bunch of 1 plus 1 dimensional fermions, and those have mass given by the transverse momentum in the higher dimensional picture. Okay, so in order to find states of the higher dimensional fermion with a big negative energy, we could just look at these modes one by one and say how much energy, what's the lowest energy we could have in each of the modes. Okay, so we're going to do that. And then in the end, we'll sum up all those energies to figure out what's the lowest energy that a 3D Dirac fermion could have. Okay, so in order to answer this question, to explore the general states of a quantum field theory on an interval, what I'm going to do is use a regularized version of this quantum field theory. Okay, so now we move to a finite dimensional Hilbert space. And I think about a lattice for this that's going to describe my 1 plus 1 dimensional massive Dirac fermion. So I have n sites. And on each of those sites, I'm going to have 2 fermions. So creation operators A dagger and B dagger on each site that I write as a vector C dagger, and usual commutation relations for fermions. And then I choose a Hamiltonian for this system, which has an on-site term and then some nearest neighbor interactions. Okay. And so basically this Hamiltonian is chosen so that if I thought about the situation with an infinite lattice or a periodic lattice, then I choose this Hamiltonian so that I get a dispersion relation that matches with the Dirac fermion one for small values of the momentum. Okay, so the way to get the continuum limit from the lattice, we're just going to look at the long wavelength physics. And so for this particular set of numbers here, if I set, say, the transverse momentum to 0, then I get this dispersion relation. Okay, so you see that for small values of the lattice momentum, you get this Dirac cone. And if I add this term, so for the non-zero transverse momenta, what happens is I get like a little bit of a gap there. The 1 over n here ensures that in the continuum limit, we end up with the right behavior. You just get this massive Dirac fermion dispersion relation. Okay, so there's this lattice theory labeled by a parameter n. And what I could do is ask my question for particular n's in the lattice theory. And then in the end, I'm going to take n to infinity and see what we get. Okay. All right. So our question was, what's the least amount of energy that I could have if I think about any possible density matrix for the degrees of freedom on this lattice? What's the least possible energy I can have? I have to be a little bit careful because if I literally just look for the ground state of this Hamiltonian, it turns out that most of the negative energy is sitting right at the boundaries. Okay, so I actually wanted to have uniform energy throughout the interval. And so I'm going to impose that as a constraint. Okay, so I'm going to impose that we have uniform energy throughout the interval and ask what's the least that could be. Okay, well, to do that, I'm going to just slightly generalize the problem and tell you about a method of answering that question that actually applies. It's a very general kind of question that you could ask in quantum systems, and this method would apply quite generally. Okay, so given some quantum mechanics system and given some set of operators, okay, in this case it's going to be the energies associated with each site. We can ask, which values of those operator expectation values are possible. Okay. So now if I take any density matrix for this system, I could just compute the energy, this set of energies. And, then I could just explore the space of density matrices for the quantum system and see if I can see which values of E I can get. But that's pretty hard because this is such a huge space. Okay, the space of density matrices for the system of n fermions. As you know, it gets rather large rather quickly. But there's a trick for this particular question that I'm asking, which ENs are possible. There's a trick that allows me to search through a much, much smaller space. Okay, and so the trick, I don't know, maybe this is familiar, but anyways, the trick is, if there's any state, if there's any density matrix for that system where you have energies En, then there's also going to be some maximum entropy state, so maximum entropy density matrix with those same energy expectation values. Okay, so you know, if I have a state, it has some entropy, that could be the maximum entropy, but then there might be some other state with a higher entropy that has those same energy expectation values. Okay, so if I want to ask which energy distributions are possible, I could restrict my search to the space of maximum von Neumann entropy states. Oh, that slide got messed up. Okay, I'll just tell you. So if I want to do that, I can ask, well, what sort of density matrices are those that have the maximum entropy with particular expectation values for a set of operators? And so what you would do to find those density matrices is extremize the von Neumann entropy and then include some Lagrange multipliers that set the expectation values for your set of observables to the values that you want. Okay, and there's another Lagrange multiplier that sets the trace of the density matrix to 1. Okay, and the result of that extremization procedure is that the kinds of density matrices that maximize entropy subject to a constraint that various observables have particular values, well, those density matrices are always of this form. They're the exponential of some linear combination of the set of observables that you're interested in. So in our case, the set of observables that I'm interested in are the energies associated with each of the sites of this lattice. And so I need to consider density matrices of this form. Okay. And so now we're just, you know, if we have n sites, we're now just exploring an n-dimensional space of values of these beta parameters. Okay, and then we can ask, can we choose those beta parameters to get the energy that we want? So because we're working in a very simple quantum system, it's just a free field theory. It turns out that like starting with a set of beta parameters and computing the energy for such a density matrix is a pretty easy problem. And so we can do this numerically. And then we could try to numerically vary the betas to get the energy that we want. Okay, so more specifically, suppose we want to ask the question, is a certain distribution of energies possible? Well, then we could define this cost function, which is the energy that we want minus the energy that you get for a specific set of betas, sum of that squared. And then you could just try to minimize this using some gradient descent, or actually it turns out this Newton method works pretty well if you know what that is. Okay, so we can do this numerically. And so summarizing that procedure, okay, we have this space of energies. This is E1 is the energy at the first site, E2 is the energy at the second site, and so forth. And we want to know which of these values are possible. And so we minimize, that's a region in the middle here where this cost function, where the minimum of the cost function is 0. Okay, and so we could basically map this out. We could numerically, we could take a point and figure out if we're in this region or not. And so this turned out to work pretty well, and it was not hard to do, say, up to 100 fermions. Well, originally for me, it was hard until I learned various tricks, but in the end, it wasn't too hard. And so I can now show you some results. Okay, so again, what are we doing? We have this lattice of n fermions that's a lattice version of our massive Dirac fermion for various masses. We're looking at states of this form, density matrix equals e to the minus beta nhn. And we're trying to have all of the energies be equal and as small as possible. And so that problem has a particular solution. So there's a particular set of betas that give you this least possible energy, and it's different for different masses of your Dirac fermion. But you seem to get, as the number of fermions becomes large, there's a limiting shape that you get for these betas. Okay, so like in general, you want to make all the betas fairly large, but there's a particular shape. And so that suggests that you're getting to some continuum state. And it's a special kind of continuum state of the Dirac fermion where we would say the modular Hamiltonian is local. So the log of the density matrix for your field theory state is just this integral of some function beta of x times the T00 of x. So it's like a generalization of the thermal state, which would be beta times the integral of T00 over everything. I think there should be a minus sign here. So there's this particular kind of state. And then what's the energy that you get? So now we have, for each mass, a minimum possible energy density. And I've plotted that here. So the data points are this minimum possible energy density that you get for various possible lattice. So let's see, I don't know, blue and then red and then yellow. And then those are larger and larger numbers of sites. And you can kind of extrapolate that to get some n equals infinity result. So that's the purple dots. Okay, so the purple dots are the least energy that you could have for this massive Dirac fermion as a function of the mass. Okay, and now this green curve is a known result, and that's the known result for the energy of a one-dimensional fermion with these anti-periodic boundary conditions. So that's for some known boundary conditions that give you negative energy. And we see that actually our numerical procedure for zero mass, it gives you exactly like within 0.01% of that answer for the anti-periodic boundary conditions for fermions. Okay, so for a massless Dirac fermion on a spatial interval of length L, the least possible energy you can get is basically this thing where you identify the two sides of the interval and have anti-periodic boundary conditions. But for the massive cases, you can do better than the anti-periodic boundary conditions. Okay, so you see this function with the anti-periodic boundary conditions, it sort of decays exponentially to 0. But our results for just the least possible energy, they are a function that decays more slowly. Okay, so what are the implications of that? Remember, we were modeling our 3+1 dimensional Dirac fermion as a collection of these 1+1 dimensional fermions with various masses that were equal to the transverse momentum. So to get the answer for the least energy in a 3+1 dimensional Dirac fermion in a slab, what we need to do is add up all the contributions of these different modes. Okay, so we have to integrate over k of basically this function. If you do that for the if you do that for the green curve, for the thing with anti-periodic boundary conditions for all the different masses, you reproduce this number -7 pi over 180 that I told you before. But if you do it for the actual minimum energy state of each of those modes, then your integral seems to diverge. Okay, and that's because this is like a power law fall off that's slow enough that when you put it in this integral, it gives you -infinity. Okay, and so the net result of all that, if you dozed off for a few minutes, what we seem to find is that for this very ordinary kind of field theory, a massless 3+1 dimensional Dirac fermion on a slab, affixed with L, it seems that there exist states with arbitrarily small uniform energy density relative to the Minkowski space vacuum. Okay, so there is no limit. And now just a review of why we care about that. Why did we even look for that? And this will be the talk summary as well. So we were interested in cosmology, and we noticed that this large class of negative cosmological constant cosmologies, some of them possibly realistic, have an analytic continuation to an asymptotically ADS wormhole geometry. And so this suggested that maybe a state of a cosmological theory could be defined holographically using the ADS-CFT correspondence. But if this is true, this blue geometry, this wormhole geometry should exist as a valid solution. And that required a weird field theory phenomena that was not previously known to exist, that fields in asymptotically ADS spacetimes could have these extremely large negative energies. Okay, so extremely large negative Casimir energies. So we then went out and looked for this weird field theory phenomenon in a simple free field model. And it seems that it exists, that actually there are states of quantum fields on spaces with boundaries where the energy density relative to the Minkowski space vacuum can be as low as you want. Okay, so I'm a little bit over time, but that's all I have. Thanks for listening.
Yeah, please.
This is fascinating. I would like to know how possibly is it to generalize to the case when you have a asymptotically flat space-time, and also what about the cases with boson?
Yeah. Okay. So I think it shouldn't be too hard to investigate free bosons in the way that we did here. I'll mention one other paper that is relevant to this last investigation. So before we studied the free fermion on the slab, we also did an investigation of holographic conformal field theories on the slab geometry and asked the same question of what's the least energy density you could get. And so there, what we found was that if you take some field theory on a slab and then couple it to another field theory outside the slab with a particular kind of interface, okay, we found that if the field theory outside has less degrees of freedom and the interface has certain properties, then again, you get this result that there's no limit for how low the energy density can be inside the slab. So that's another example where probably your field theory has both fermions and bosons. But I think it would be interesting to just do this direct study of a bosonic free field theory and see for that, how low can the energy be? About your other question with asymptotically flat space times, I'm not sure whether this approach is going to be useful. I mean, other than the usual thing where we could imagine defining asymptotically flat space times as some limit where the cosmological constant goes to zero or the curvature goes to zero. But I don't think I have anything in particular to say about that case. But again, this is spatially, so these cosmology are spatially flat. So just like our own universe observationally seems to be spatially flat.
Then I think we have a question on Zoom.
I have.
Oh, yeah. Oh, let's first have the question on Zoom and give.
Okay, sure.
Yeah. Okay, please.
Oh, okay. Sorry, is it my turn?
Yes, yes.
Okay, thanks. Didn't mean to jump in. But I'm wondering, it seems like this 3+1D lattice fermion model is something that you could maybe actually find in the lab. So would you say that there's kind of an experimental realization if you could prepare these states that you would actually be able to observe this negative energy with?
Yeah, this is a really interesting question. I mean, I think there's no reason I mean, it's not totally clear how you prepare these states, and I'm not an expert, but certainly because it's such a simple system, and we know basically what the state is, it's definitely a question that you can ask, and probably there are people that know more about what you can do experimentally. But yes, I think this is a very interesting thing to try to set up. Even with, I didn't really mention the 2+1 case, but you could also get the answer for 2+1, and there it seems like we get this particular finite number for what the minimum negative energy is. So again, that might be something you could look for in a experimental realization of 2+1. But actually, even just like looking at 1+1 dimensional lattice fermions, if you can set that up, you can try to somehow reproduce the states that I'm talking about, and there's certain numbers that are predicted here. So you could just see, can you get those numbers out of a particular state. But again, I'm pretty naive in terms of what you can actually do. But yeah, it totally seems interesting, and I'll probably be talking to Brian about that.
Cool.
Oh, hi, Mark. Thanks for your talk. Actually, I'm interested in exactly this picture of the Big Crunch cosmology and the ADS Lorentzian wormhole, though this is good. It has double analytic continuation. My question is, like, it seems like the time-like trajectory here becomes the space like some space condition on the Cauchy slice, and especially in that ADS Lorentzian picture, the boundary condition is actually from one of the boundary trajectory evolution here. So I was thinking, okay, it seems like a boundary trajectory evolution in this Big Crunch university should obey some certain evolution property, because this is time trajectory generated by some Hamiltonian. But if you analytically continue back to ADS Lorentzian picture, then it just gives some very specific boundary conditions. And I was wondering if there is any consistency check here, or like, would you say this thing should have some other constraints so that when you analytic forward and back, both of the conditions are consistent?
Yeah. Okay. So, I think. I mean, I got the gist of the question. I think I can address that by maybe emphasizing that the states that we get in this way are fairly special states. So the kinds of states that come out of this are highly constrained. So I think if you took like a kind of generic state of a quantum field theory on this cosmological background, and you tried to do this, you tried to ask, is there some analytic continuation that makes sense? Then probably generally it wouldn't really be sensible. So like even in quantum field theory, if you take the vacuums, the Minkowski space vacuum, then there the observables have a nice analytic continuation to observables in a Euclidean field theory. But if you took kind of more general states of a quantum field theory on Minkowski space, then you wouldn't generally expect anything nice to happen with the analytic continuation. So I think this is kind of a highly constrained scenario where if you started from the cosmological observables, like the fact that they analytically continue to something is pretty special. And so in a sense, like we're going from like a huge space of possible states for cosmology to a much smaller space that would more or less be labeled by like the possible boundary conditions here for in the asymptotically ADS regions. So I'm not sure if I totally answered your question, but
yeah, that's what I expect as well.
Yeah.
Any further questions? Yes.
So you mentioned it's in a simple free field model. I'm wondering, do you expect things would change dramatically, or it will be more or less the same if we have an interacting theory?
yeah, so I think that's what the holographic calculation that I mentioned, and that was a paper with Alex May and Peter Samidja. So that was basically, studying the same question of very strongly interacting field theory that would have a gravity dual. And so we find a similar qualitative result. Actually, in that case, we seem to find no lower bound for the energy either in 2+1 or 3+1 dimensions. So it's maybe a little bit different. But since we find the same qualitative result both in the free field theory and in the holographic strongly interacting field theory, I would suspect that even for sort of a perturbatively interacting theory, you could also get similar results. So yeah, I should just say with the holographic calculation, we were using what's called a bottom-up approach, which is just to define some kind of classical gravitational theory that's dual to the field theory. It's not really guaranteed that there's a specific well-defined microscopic quantum field theory that you're studying. And so that was one of the reasons why we followed up by this explicit field theory calculation. But usually these holographic studies can give you some reliable, at least qualitative information about what's possible in strongly interacting theories.
That's fascinating.
Any last questions? Okay, if not, then let's thank Mark again for nice work. Yeah.